Okay, Bismillahirrahmanirrahim. So suppose today's lecture is the continuation from the Tuesday lecture. So on Tuesday, we already stopped at Dijkstra algorithm. So hopefully all of you already know how to find the shortest path by using Dijkstra algorithm and also Prim's algorithm. So the next algorithm is called as Floyd's algorithm. So if you notice in the slide, Madam also provide to you the additional video, okay, from the other lecture lah. So after this, if you still not understand on Floyd's algorithm, so you can refer to this YouTube link, okay? So, Bismillahirrahmanirrahim again. So, Floyd's algorithm, guys, actually is purposely for directed graph. So, if you notice before this on Tuesday, all of the graph are undirected. There is no arrow at the edge of the graph kan. So, Floyd's algorithm ni, we use it to solve the problems or to find the minimum or shortest path of the directed graph. So let's look at the how Floyd's algorithm is being used. He said that for any pair of vertices Vi and Vj must be element of V lah. So and then consider all paths from Vi to Vj whose intermediate vertices belong to the set of V1, V2 and Vk. So of course you have to make sure all the nodes and edges too must be inside the graph. Okay. So and then one important thing that you need to consider is the PK ni PIK. So PIK ni is actually stands for iteration. So let's PIK and J ni of weight DIKJ be the minimum weight path among them. So we need to construct the matrix when you got the graph. So the first step is to construct the matrix and fill in the initial value for all vertex. So you have to consider from A to B, A to C and the rest of the node. Okay. And then you fill in the matrix table. Okay. So it said that if vertex Vk ni is not in the shortest path from Vi to Vj, then no need to change the value of the initial values matrix that you include in step 1. So you just remain the value, okay, maintain the initial value from the matrix. Kalau if the vertex Vk is the shortest path, maksudnya value dia lagi rendah from the original value, so you need to modify the value of the matrix tu So if Vk is in Pikj ni, then we can break up the Pikj into two paths. Okay, so kalau dah habis or if we cannot extend the first path of the graph, so we can break up to another path lah. We can find another path to find the shortest path. Okay, so this is how the Floyd's algorithm expand the graph until the end of the vertex. So, for example, if given to you 5 nodes, okay, of the graph, so you have to consider 5 iteration, 5 looping or 5 steps to consider in order to find the shortest path from A to Z, for example. So, and then the iteration is based on the number of nodes. Then you have to consider how many number of nodes. Then you need to stand by the iteration or the steps. Each iteration refer to one node where you need to identify whether the other nodes can go through to its destination by the current node in the iteration. Macam mana nak cerita So kita tengok contoh lah senang guys. Okay, so this is the algorithm first. Before we look at the example, okay, this is the algorithm on how to calculate the shortest path. Alright, and then actually is in serial process. So, but there is some iteration that we can do in parallel. Okay, so this is the algorithm. Okay, before this, we look at the formulation, how to find the shortest path, and then include the shortest path into the algorithm. Okay, so this is the parallel formulation for Floyd's algorithm. Alright, and then you need to construct the matrix, and then you need to update the value. Okay, each processor can implement for each iteration. So these are the general process to implement the Floyd algorithm in parallel processing. Okay, so this is how the Floyd algorithm is being illustrated using 2D block mapping. Okay. So you just need to know how does the Floyd's algorithm is being executed. So yang ni you just tahu macam gitu-gitu je. Okay, so this are the parallel formulation using 2D block mapping. Okay, dia punya algorithm. Okay, and so on. So madam nak tunjuk dia punya jalan kerja. So actually, okay, so let's look at the question first. So this is the question given to you. So the question asks you to solve or find the shortest path using Floyd's algorithm. So we have 4 nodes here, A, B, C, and D. So just now we know that if we want to implement Floyd algorithm, so we need to consider the iteration, right? So how many iteration here? So we need to look at the number of nodes. So basically ada berapa anak-anak? Ada 4 iteration yang kita kena buat. Okay. So how to solve this? So let's look at the answer. Okay. So first of all so pada siapa-siapa yang nak snap ke screenshot ke, kalau ada soalan boleh tanya Madam direct. Okay, so it said that the first step you need to draw back the question, okay, the graph. Okay, there are 4 nodes here. And then from this graph, you need to construct the matrix table. So column and row. So you need to fulfill all the value from node A to B to C and D, and for the rest one lah. Okay, so let's look at one by one. So from A to A, of course there is no A to A, so we include 0 here. So from A to B there is a value which is 4. So you just fill in the 4 into the matrix table. So and then from A to C. So A to C, okay, there is an H between A to C. The value is 3. So include 3 here. And then there is a path from A to D. Then you include 7. So then we move on to the next one, which is B. From B to A. Ada tak from B to A? Tak ada. So in this case, you cannot put 0 into the table, but you need to include an infinity. Okay, anak-anak, infinity for any path that there is no edges between the nodes. So between B and B, we include 0. And B and C, is there any vertex or edges between B and C? B bagi C, tak ada kan? So kalau tak ada, you include infinity. So from B to D, there is an H between B to D, and then you include 5. So you need to fill in all the value, original value from the node A to node something lah. Okay. Yang ni clear ke? Nak? Boleh ke yang ni? Okay, so this is the first step. Second one, you need to tell the working answer. You need to write where this is the first iteration. K equals to 0. Ni yang tadi DIK tadi tu. So K equals to 0. And then you need to write down all the possible distance. So from A to B tadi, ni semua ni make sure ada value dia dalam table. Okay. Clear? So yang ini initial distance. So maksud initial distance, there is an edges from the node to the closest one lah. So let's say yang ni A to B, A to C, terus tulis A to D. And then what else? B to D. Ada lagi tak keluar daripada B? Tak ada kan? So proceed to the C pula. C to B ada. C to D ada. How about D? Ada tak any arrow or edges out from D? Tak ada langsung kan? So no need to write down the distance. So just write down the available or current distance for K0. Why K0? There is no current node between the first node and the next coming or the closest node. Clear step 0, anak-anak? Step 1? Okay, so next one, what you need to do is, okay, so you have to consider after K0, of course, K equals to 1. So K equals to 1 ni, in this case, our node is ABC, right? So you need to make sure, is there any distance that will go through node A? So K0 ni actually equals to node A. So kalau you tengok kat sini, please refer to the arrow. There is no distance yang go through node A. C go through node A ke? Tak ada kan? So how about D? Dia go through node A ke? No. How about B? Go through node A? Tak ada. So tak ada. So you need to write down, there is no shortest path found through vertex A. If this situation happen, okay, no need to modify the original value of matrix. So you just maintain this matrix lah, value. So kalau you tengok 473, 059, and then you just write down again the matrix with the current value. Clear step 2, anak-anak? Okay, kalau tak ada soalan, kita proceed to the step number 3. Okay, step 3 is K equals to 2. Iteration number 2 or iteration 3 lah. So K2 sebab kita start from 0 tadi, K0 kan. Okay, so iteration 2, K equals to 2. So after A just now, we need to find is there any path or distance yang go through A. Right now, kita kena go to the next one is any distance yang go through B. Kalau you look at the arrow, there is a few distance yang must go through node B. So you need to find the possible distance lah. So, madam kalau you all tengok sini tu, saya lukis balik. So A dia go through B untuk pergi ke D. C go through B nak pergi ke D. Okay. So itu maksudnya. Macam mana nak tahu? Kita kena tengok consider the original graph. Okay. So you need to write down the distance. So from A to D tadi. So dia go through B, right? So so A to B to D. So you need to write the path. So A to B is 4 plus dengan B to D is 5. Where do we get this? From the original table. A nak pergi ke D kena melalui 4 and 5. So that's why our answer is equals to 9. After you get the distance equals to 9, you need to refer back to the table. So A nak pergi D ni original value dia berapa anak-anak? 7. So you need to compare the latest one that you get, which is 9. Is it smallest or largest compared to the original value? So original value is 7. So 9 of course is larger than 7. Do we need to change or modify the table? Tak perlu. Kita hanya modify the table if the new or latest value ni is lesser than the original value. So maintain A pergi ke D melalui B ialah 7. Tak perlu ubah. So next one is C wants to go to D melalui B. So C, B, D. So C, B, D which is 6 plus 5. How we get this 6 plus 5? C pergi B is 6. B to D is 5. So that's why 6 plus 5. So equals to 11. So 11 is larger than the original value. C go to D is equals to 9 here. So you compare 11 and 9. So you get 11 is larger than 9. So do we need to modify the value? No need to modify. So just maintain the original table. So habis dekat step 3. Kalau dah tak ada go through node B, now we need to consider go through node apa pula anak-anak? C pula lah. Okay, so K equals to 2. K 2 or 3 guys? 3 lah kan? Sebab Madam dah tersilap tadi. Sini K3 ya. Okay, so K3, there is only one distance. A to D go through node C. So A to D go through node C which is equals to 12. 3 plus 9. So 12 is larger than 7 dan larger than origin. So no need to modify. So there is another one which is A nak pergi B. A nak pergi B. Mana A nak pergi B? A pergi B ada melalui C. So you need to add another one. So A go to B through C which is 9. 9 is larger than 4 than origin. So no need to change. Okay. So step yang seterusnya, after C, we need to consider the D pula. So D ada tak go through node D nak pergi ke mana-mana? So tak ada basically semua nak pergi dekat D. So kalau tak ada, just write down no shortest path through vertex D. So kalau habis semua, so K suppose equals to 4 Sembilan silap. So the final shortest path, kalau you all tengok, ada tak kita ubah apa-apa? Tak ada kan? So you just write the original value. So then the final one, you need to write this one. Another matrix table where you need to write down the current vertex ataupun go through vertex. So let's say A nak pergi B, dia kena melalui vertex apa, node apa. So A pergi C, apa-apa and so on lah. So B nak pergi D, yang mana. So ni nak pergi mana, ikut mana. Macam mana nak tahu? So refer to the value. How you get this? Then you will get the nodes. Okay, go through from where to where. Okay, that one is Floyd's algorithm. Any question on Floyd algorithm? Ya, saya. Yes, betul. Dia bukan sahaja counter tau. Dia merangkap counter, dia merangkap kita nak go through to node apa. Okay, so kalau you perasan, tadi counter 0 ni sebenarnya untuk node yang pertama A ni. So same goes with counter 1 ni. Dia nak pergi ke ni pula kan. Go through node B, D and so on. Okay. So Floyd ni yang pentingnya dia counter tu. Betul? Counter. Salah counter, salah cari yang macam Meda tadi, kalau you notice ni semua Meda tulis pencil, tiba-tiba Meda ternampak yang ni ada satu tertinggal. So tu problem dia, kalau kita tersilap mungkin nilai dalam teks ni, dalam matrix kita akan silap lah. So ada yang buat jawapan, dia tulis yang ni asal original betul, tapi at the end yang ni semua salah. So jalan kerja dia sebenarnya yang betul yang atas saja. The rest silap sebab dia tertinggal 1-2 step. Okay? Ada soalan lain? Tak ada So clear Okay. So kalau clear, kita proceed to the next one. Okay, so Floyd algorithm actually can be speed up. Instead of using parallel just now, you can also use pipeline approach. So semua tu speed up lah. Sebab apa? Kalau you tengok, dia by iteration, right? The Floyd algorithm. So if by iteration ni, is it logic if we can use the pipeline or parallel? Because we need to wait the output from the previous step, right? So at the end sebenarnya all the graph algorithm ni is being executed by using serial formulation, serial execution. Tapi laju macam mana? Kita depends on our processor. Actually semua serial. Nampak je macam parallel. So maybe there is one step or two step that we can implement parallel. Mungkin dekat pada first initial value that we want to find the matrix for the first one tu kan, then we can implement parallel until that level only. So the rest maybe we need to apply serial processing. Okay, so that one is Floyd. So this is the slide to compare the maximum number of processes for each algorithm. So Floyd ni ada 1D block, 2D block, ada pipeline, ada banyak lagi lah. So depends on the programmer on how they want to write the formulation for this graph algorithm. Okay. So kalau you tengok kat situ yang n-log ni dia makin laju lah sebenarnya. Okay. And then next one we move on to the transitive closure. Transitive ni kalau kita belajar in maths, transitive ni we create a new graph. Okay. In this case, if G equals to VE is a graph, they create a new graph. It is called as transitive closure of G. Is defined as the graph G star ni. This is the new lah, the transitive graph. Okay, how they make the transitive? Dia tambah H, E star. So where E star equals to VI, still in VI and VJ lah. Maksudnya apa? Dia create a new path from vertex I to J. Okay. So the connectivity matrix of G is a matrix A star equals to A I star J and so on lah. So that one is called as transitive. Okay, so this is the connected components. Okay, so what is meant by connected components? Actually, is composed of undirected graph. The equivalence classes of vertices under the is reachable from the relation. So ini another example of connected components where several nodes is being connected together, but the edges is from undirected edge. There is no direction from each from node to node. So a graph with three, this is an example graph with three connected components. Why three connected components? Node 1, 2 and 3 are connected together. Node 2, 3, 4 connected together and so on lah. 5, 6, 7 and I don't know why the slide tell this one. 9 and 8 ni is 3 connected components. Obviously it's 2, right? Maybe there is some mistake here, right? So connected components, okay, by using depth first search based algorithm. I'm sure that you already learned this in 645. Okay, So you may use depth first search based algorithm to find the shortest path. Okay, so you can perform this on the graph to get a forest. Okay, each tree in the forest correspond to a separate connected component. So if you still remember, kalau ada banyak tree, you can get a forest, kan? Okay, so part B is a depth first search forest. B yang ni obtained from the DFS. Okay, from A ni. So from A you can derive the graph B. So dia ada macam dia traverse by depth first search ke bawah dulu Dia bukan breadth first search, dia depth makin ke bawah. So that's why kalau you tengok ada edge yang tak join, right? So each of these trees is a connected component as long as they are connected together between the node. Okay, so A and B. Okay, another example of that first search based algorithm. So for your own information, it's not necessary for us to implement prims ke, jigsaw, floor and so on. So it depends on the algorithm that you use. As long as the algorithm can find the shortest path and in a quickest or fastest way lah. Okay, so this is the parallel formulation for connected component. Alright, dia buat partition the graph across processes. Okay, so to make it parallel, of course we need to do some partition lah, or else kita implement serial formulation or serial process. Okay. So macam mana dia nak merge balik ataupun macam mana dia nak get the output from all the parallel process. Last kali at the last level dia akan merge sampai dia dapat satu minimum spanning tree MST yang kita dah belajar awal-awal Okay, so another example, the formulation on connected component. Okay, assume this is the graph, the original graph, and then from the original graph ni dia divide by 2 dia apa nama kita panggil tu? Dia decompose. Dia pecahkan, dia divide into 2 process. Yang atas 1 until 3 ni processor 1 yang cover, 4 until 7, okay, then the rest of the processor yang cover Okay, so if you look at the explanation, so the adjacency matrix of the graph G in the A ni sebelum dia nak buat formulation of parallel, dia partitionkan dulu So bila dia dah partition, each process gets a subgraph G ni, C and E ni, okay, dia akan dapat yang ni. Okay, subgraph yang ni set 1, yang E ni set yang ke-2. Okay, each process then computes the spanning forest of the subgraph D and F. So finally the two spanning tree are merged to form the solution. So before dia nak cari the shortest path tu, dia decompose dulu. Okay, from CE ni dia jadi D and F. So to get back the answer, dia kena combine balik So that's why dia kata tadi dia kena merge to get the result of the path graph ataupun to the shortest path. Okay, so these are the parallel formulation to merge pairs of spanning forests efficiently. So actually this is not covered in the final exam or test lah So just for your own information So they use the function find x and also union x, y. Okay, so dia ada guna join, disjoin operation in order for them to make the decomposition and also to join back. They want to merge the graph again. Alright, so the parallel formulation lagi to merge the graph that they have decomposed in the earlier stage. Okay, And then dia guna union operation and so on lah. Okay, to merge the graph. Okay, what else? Parallel 1D block mapping. Okay, payahlah ni you all. Okay, and then the formulation to find the cost optimal formulation, whether the formulation or the algorithm is efficiency or not. So they calculate the cost optimal formulation by using this formula. Okay, and then this one is the algorithm for the sparse graph. A graph G equals to VE is a sparse graph if E is smaller than V. So E is the edges, V is the vertex. So kalau you jumpa macam ni, this kind of graph, it is called as sparse graph, where the nodes, okay, is more, the number of nodes is more than the number of edge, okay, the connection. So this is an example. Okay, this is a linear graph. Okay, and then linear graph kalau tengok dia ada banyak vertex instead of edge. Dia ada dua saja edge. Okay, and then B, a grid graph. Okay, is also known as sparse graph. So each of the set tu contains 2 edges and 4 nodes. So yang C, a random sparse graph. Okay, random. Why random? Because it's scattered. Okay, it's not an ordered graph lah, like grid ni, jadi dia macam susun cantik So ni dia adalah randomly ordered. Okay, it is called as sparse graph, where node lagi banyak daripada edge. Kalau yang ni you nampak obviously lah, node lagi banyak daripada edge yang connected together Okay, so this is the algorithm for sparse graph, dense algorithm. Okay, it use dense algorithm and then use adjacency list instead of an adjacency matrix. So ingat lagi tak, list, dia list all the nodes and also the connection between the nodes. Okay, so that one is adjacency list. Parallel algorithm typically make use of graph structure or degree information for performance. So if we want to make it parallel, so they need to identify lah. Okay, and then make use of the graph structure tu. Okay, to look at the performance, whether it's good or not to be implemented in parallel formulation. Okay, if not, no need to implement parallel lah, just use serial formulation. Okay, so another example, this is a street map. Okay, street map ni it can be transformed into sparse graph. Okay, so kalau you tengok kat sini how they make a connection by a single dotted yang ada dekat street ni This is the intersection between node and node lah. So from this they transform to this one So kita akan nampak lah. So how to calculate the shortest path from this. Okay, kalau kita tengok yang ni kita tak boleh nampak. So kita transform to the sparse graph. Then we know what kind of algorithm that we can implement to find the shortest path between the node or vertex. Okay. So next one is finding a maximal independent set. So a set of vertices I is subset of V is called independent if tak ada pair, no pair of the vertices. Let's say between A dengan C ni, there is no pair. Dia tak ada connected together So melalui H. So kalau between A, B and E ni, of course there is a pair. So kalau ada pair, kita tak panggil dia independent lah. So an independent set is called maximal. So independent tadi, let's say A ni is an independent between A, C, G, F and J ni, dia akan dipanggil maximal jika including any other vertex not in I. So the independence property is violated. So if you can see here, independent set is a set of node that is not connected together. Independent kan? So dia tak ada connection. So it said that kalau set ADIH, A, D, dia tak ada connection. Between A dengan D, there is no connection. Between A and I, okay, I jauh, so tak ada connection. So H, okay, tak ada connection. So that one is called as independent set. So from this set, we can identify whether is it maximal independent set or not. So kita kena tengoklah. Okay, ada vertex dalam set yang asal ke tidak. So in this case, C, J, F, G ni is not include inside the independent set, right? So that one is called as maximal independent set. So C, J, F, G ni adalah maximal independent set. How about this? D, H and F also known as maximal independent set. Okay. So actually it's not fixed. The set is not fixed. It depends on the connection between the node that you have include inside the independent set. Okay. So this is the algorithm finding a maximal independent set. Okay, so you need to consider or start by MIS I to be empty dulu, and then assigning all vertices to a candidate set C. So vertices yang asal tadi kita assign to candidate C. So vertex V from C is moved one by one into set I ni, and all vertices adjacent to V are removed from C. Lama-lama C dia jadi empty. And then it said that this process is inherently serial. So we cannot make it parallel lah, because we need to check one by one. The set, all the vertices need to be removed one by one and check one by one from the vertex or adjacency vertex to be include inside the set I. Okay. So again, finding a maximum independent sets, parallel MIS algorithm, dia yang ni pakai guna parallel MIS algorithm. Dia use randomization to gain concurrency. They use Lubis algorithm. This is for graph coloring. So in this case, each node is in the candidate set of C. Macam kita cakap tadi, each node generate a unique random number and communicates to its neighbors. Why need to communicate to its neighbors? They need to check lah whether there is a connection or not. So if a node number exceed that all of its neighbors, it joins set I. Kalau tak, dia akan remove from C. So kita keep on continue this algorithm until C is empty. Okay. So this is an example. So kalau you ada this kind of graph, so assign a random number first to all the nodes. Okay. And then it said that just now each node must be put in candidate set C. Semua ni jadi candidate. And then each node will generate random number. Ni semua ni random number. And we need to check the connection between the vertex and also its neighbors. Okay, so this is the first step. So if a node number exceed that all its neighbors, it will join set I independent. All of its neighbors are removed from C. So kalau you tengok kat sini, B, step B after the second number assignment, okay tadi 1. Okay, 1 masuk dalam independent set. And then what else? 0. Okay, 1 ni dia ialah dia tak exceed, value dia tak exceed to the neighbors. Okay, dia kurang daripada value neighbors. So same goes to 0. 0 is smaller than its neighbors. So it can include or put inside the set C lah. Okay, what else? They choose 4. Okay, 4. Why 4? 4 is smaller than its neighbors. So 4 also can be included in the independent set. So for the first stage ni dia dapat 3 node to be included in the independent set. So dia assign a new node number, a random number assignment, dia set balik semula. So kalau you tengok kat tadi, yang grey ni vertex adjacent to a vertex in the independent set. So ni pun dalam independent set. Yang ni bukanlah 11, 15, so on ni Okay, then dia assign balik semula yang baru, nombor baru. Okay, so then it gets a new vertex in the independent set, right? So this one is to find a maximal independent set. Okay, so again, this one also is a random. Okay, and then it depends on the calculation and also the algorithm on how to find the random number and also the maximal independent set. Okay, so this just an example on how they want to find the final maximal independent set. Okay, so these are the formulation on how to implement the MIS in parallel process. Okay, so of course they need to use the partition to partition all the set into several number of processes and so on lah, and then they follow the step just now sampai set C is empty. Okay, so finish on MIS. The last one is called as single source shortest path. Okay, single source shortest path ni we have another algorithm named as Johnson algorithm. So actually Johnson algorithm ni is an enhancement or modification from the Dijkstra algorithm. So Johnson algorithm ni dia kita buat dia ataupun kita guna dia untuk graph yang ada negative value. So how to deal with negative value? So Johnson algorithm ni dia provide one solution where you need to create a new nodes. You need to add new nodes to the graph, then to hold or to handle the negative value. So how the Johnson algorithm do this work? It said that the modification accounts for the fact that the minimization step in Dijkstra algorithm need to be performed only for those nodes adjacent to the previous selected node. So they need to do some modification to Dijkstra algorithm. So actually Johnson algorithm and Dijkstra ni dia macam bekerjasama. Okay. So Johnson algorithm use a priority queue to store the value LV for each vertex V in element V minus VT. So madam dah simplify the process. So by looking at this step, the first one you need to add new node to the graph and give weight 0 to all paths. And then you need to calculate the new weight by using this formulation. Okay, and then have to make sure the weight that we calculate tu must be greater than or equals to 0. Then bila dah settle step 1 and step 2, we need to run the Dijkstra algorithm again because of the negative value is being removed from the graph. So I want to show you an example how the Johnson algorithm is being implemented. Okay, sekejap ya. Okay, Okay. So you can go to this link also after this if you want to increase your understanding. Okay, so given to us this kind of graph. Okay, kalau you tengok graph dia ada negative value kan. So we cannot use Dijkstra, Prims or Floyd's to handle this kind of graph. So Johnson algorithm advise us to make some modification to the Dijkstra. So that's why dia panggil Johnson. Sebenarnya Johnson dia tambah sikit dekat Dijkstra algorithm tu Okay, so if you get this kind of graph, so there is a negative value here which is negative 5. So we don't want this negative value because of course negative value will have the shortest path. So what Johnson advised us is to add new node. So suggestion dia to add new node, okay, it's like this. So kalau you tengok tu dia add new node 4 kat sini Why 4? Sebab node dia label by using number 0, 1, 2 and 3. So dia add node 4 here, tak kisahlah you nak letak dekat kiri atau kat kanan. So as long as you add new node. And then you make an edge, new edge between new source. This new node we call as new source So between the source and also the destination tu guys. So you give a new value which is 0 lah. Semua 0 From 4 to 0, from 4 to 1, from 4 to 3 and 2, you bagi nilai 0. Okay, then after you create new node, you need to calculate the shortest distance from 4 to all vertices using Bell-Manford algorithm. So bila you dah calculate, so the shortest distance from 4 to 0 ni, of course you akan dapat 0. From 4 to 5, from 4 to 1, you akan dapat negative 5 because of from 4 to 1, dia melalui node 0 ni, 0 plus negative 5 which is equals to negative 5. From 4 to 2, okay, so from 4 to 2, you akan dapat berapa? Dia akan melalui sini dia ikut jalan ni. So negative 5 plus 4, you will get negative 1. Kalau kita pergi direct ke sini, dia akan dapat kosong kan. So kita kena melalui yang ni lah. Okay, from 4 to 2, 0 plus negative 5 plus 4, which is equals to negative 1. So from node 4 to 3, which is directly 0 So you akan dapat nilai H, the new value which is 0, okay, equals to, they represent node 0 and negative 5, it's represent node 1, negative 1, they represent node 2 and 0, they represent node 3. Okay, so once you get this new value, you kena masukkan dalam formulation yang kita discuss tadi, which is WUV, this is the new weight, equals to original weight yang asal yang ada negative value tu, plus dengan HU. Where to get this? HU ni ialah this one lah. You kena get the value from this one not 0, 1, 2 and 3. HU minus HV. So let's say, tengok macam mana dia calculate. Okay. So by using the formula, WV, 0 ni, how to get the 0? Which is by taken from WV tadi. WV kita is negative 5 kan? Okay, equals to HU, okay, minus dengan HV. So HU kita is 0. HU ialah node 0 to node 1. So H0 to node 1, nilai dia macam ni nak ambil anak-anak? Kita tengok yang ni. H0, node 0 is 0. Node 1 nak pergi 1 nilai dia negatif 5. So masukkan dalam formulation WUV plus HU tadi minus HV, kita akan dapat nilai kosong. Boleh tak? Okay, Menda tunjuk satu lagi. So how to get this 0? Masukkan formula WUV HU HV ni. So WUV kita nilai asal 4. HU from node 1. Node 1 kita tadi ialah negative 5 to node 2. Value kita ialah negative 1. So 4 plus negative 5 minus negative 1, we will get 0. Boleh tak? So lagi, kalau tak nampak lagi. So how we get this 3? From node WUV tadi, nak pergi node 2, kita dapat nilai 2. Okay, and then HU kita 0. HU kita from 0 nak pergi 2. Nilai 2 ialah negative 1. So 2 plus 0 minus 1, we will get 3 and the rest. Okay, so bila you dah buat formulation WUV HU HV ni, so you will get the new value like written in blue color. So dah tak ada negative value. This is our new value. Bila you dah dapat new value, then what you need to do? The next step, you need to implement the Dijkstra algorithm. So, pakai Dijkstra algorithm, you need to create lah the new shortest path, the matrix table and so on tu sampai you dapat the last one. The last step is the shortest path or the minimum spanning tree from here. Okay, so that one is Johnson algorithm. Ada soalan untuk Johnson algorithm? Tak ada. Okay, kalau tak ada, kena buat baru tahu kan. Okay, alright. So this one is the algorithm for Johnson. Alright. And then the rest is the parallel formulation untuk implement Johnson algorithm. So if the question asks you what is the parallel formulation for Johnson, you just copy and paste this. Bukan copy and paste, maksudnya you kena jawab guna yang ni lah. Okay. And then what else? So dia dalam bentuk illustration. Ni contoh lain Tadi madam bagi yang tadi tu lebih mudah faham compare to this one nak kena masuk priority queue and so on lah. Tapi guna yang tadi lagi mudah faham. Okay. And then this is the another formulation. Okay. Panjanglah cerita dia. Alright. And then and so on shortest path and so on ni di implement Dijkstra algorithm. Okay. Habis on parallel algorithms of Johnson algorithm. Okay. Any question? Tak ada?